All right, chapter 15.11 is really the heart and soul of this chapter, and that is the Diels-Alder reaction. Diels and Alder, it's named after them. They came out with this reaction, I believe in the 20s or 30s. They got the Nobel Prize in 1950 for it. It's a very big reaction. It's a very common reaction. It's a reaction that can make very complicated ring structures, starting with very easy starting materials. What the story is that there was another group that did some chemistry, and they published a paper, and they were doing a different type of reaction, but as a side reaction or side product, they mentioned it very briefly in their footnote that they got this side reaction and the side product, but they didn't really do anything about it. And Diels and Alder read the footnote and thought that was very interesting, so they went ahead and explored kind of what that footnote was on that paper, where that other group didn't really think anything of it and they didn't really care about it, and it turned out to be this reaction. This actually turned out to be much more interesting and exciting than the original paper that guy did. So it's not that they stole the idea, it's just that the other group, they didn't want to explore it, and Diels and Alder thought it was interesting. They explored it, and it was kind of by chance that they were able to get the credit for it. And honestly, I don't even know who the other person was who actually originally found it, but they are nowhere like mentioned. But what this reaction involves is a diene, so a compound with two alkenes. So remember, a diene is something that has two double bonds, and it has to be conjugated. It's got to be a conjugated system. And a dienophile, meaning something that wants to react with a diene. And this term just came about because of this reaction. And it's something that's very electron deficient. Okay, your diene has a lot of electrons, and it wants to share it with something that does not have a lot of electrons. So those are the two things that you need in order to have a Diels-Alder reaction. And you always produce a cyclohexene out of the reaction. All right, you always form a six-membered ring with a double bond. You take two compounds that do not have rings, and they form carbon-carbon bonds. Remember I told you last semester, carbon-carbon bonds is the holy grail of organic chemistry, carbon-carbon bonds. You're making a carbon-carbon bond and ending up with some sort of a cyclohexene at the end of it. Okay, so this is kind of a big reaction. All right, the Diels-Alder is what's called a 4+2. And the reason is because your diene always has 4 carbons, and your dienophile must have 2 carbons. So that's where your 6 is coming from, 4+2, your 6-membered ring. So it's a 4+2 reaction. You're adding 4 carbons onto 2 carbons for a 4+2 cycloaddition. Again, it says because a ring is formed by the interaction of the 4 pi electrons of the alkene and with 2 pi electrons of the alkene or alkyne, depending on if your dienophile is an alkene or an alkyne. So here is the general mechanism and the general reaction. All right, here is your diene. Okay, here's the diene. Here's a double bond, single bond, double bond, conjugated. This is the electron-rich part of it. Here's your dienophile. All right, just some sort of double bond. This could also be a triple bond, but you have to have some sort of pi bond. The W stands for electron withdrawing. The W implies withdrawing. So this double bond is somewhat electron poor. So having something electronegative here, or another pi bond, an oxygen, a halogen, some sort of pi bond of some sort will withdraw electrons away from this pi bond, making these carbons much more partial positive, making this pi bond much more partial positive, so these electrons can actually share. It's what's called the concerted mechanism. It's a one-step reaction. So what basically happens is the carbon here with its electrons, let me grab my pen so we can redraw these arrows again, and the arrows are showing the mechanism. Basically the electrons here in the carbon start forming a bond to this carbon right here. Okay, so you start forming a bond here. All right, so your bond here, so this bond right here is from this bond formation. These pi electrons pop down between these two carbons. This is why you have to have a conjugated system, because you kind of have to have these, it's kind of like a resonance structure to give you a double bond here, and then these pi electrons and this carbon bonds to this carbon. So this carbon here starts forming a bond with that carbon right there. So that's what that bond is. So here's your here's your 1, 2, 3, 4. There's your 4, and then here's your 2. Okay. Now we're going to talk a lot about this and what makes a good diene, what makes a good dienophile, what makes a good W. We're going to change these groups around. You don't have to have hydrogens. You can have lots of different groups all on here, but this is just the basic reaction, just to give you an idea of what the reaction is. Okay, so you take two very simple compounds and you can make a 6-membered ring out of it. Okay. Now stereochemistry, we're going to talk a lot about stereochemistry because there is some stereochemistry outcome from the Diels-Alder reactions. Here are just some examples. All right, here's a diene. This has 2 methyl groups on it, and then here's your dienophile. So notice we have a double bond next to a triple bond. This is more electron withdrawing, your nitrogen, so it's making this very electron poor. So you're going to form a bond here and a bond there. That's your 6-member ring. Part of this chapter, it's not a hard reaction. It's just sometimes being able to see what's going to form. So this goes to this carbon, these pi electrons go here, and these electrons in this carbon form a bond right there, okay, to form that compound. Okay, notice 6-membered ring with a double bond, and now you have all these groups. I mean, this by itself, trying to make this compound without the Diels-Alder reaction would be very hard to do, extremely hard to do. But the Diels-Alder reaction makes this incredibly easy. Okay. Here's another one. This time, so here's my diene, but notice it's closed. So here I have 2 hydrogens on my diene. Here my diene has a carbon on it. So, and then I'm adding it to a triple bond. So in this case, you have this carbon forming a bond to there. These pi electrons go here, and these pi electrons are going here. This carbon right here kind of comes up. That's what this is. It's called a bridgehead. These are very interesting compounds. They're stable. But what's basically happening is this green diester is coming underneath the diene, and it's kind of popping that up. So if you want to look at there are, on the next few slides, we kind of talk about the stereochemistry of this, but imagine here is that diene. We will also go over this in class. All right, I will bring models, you should bring a model set, and we will definitely show the 3-dimensional of this. And what's happening is your triple bond, I'm just going to put the triple bond here, is coming underneath. So imagine my diene is kind of going over and the triple bond is here, and you're kind of starting to form your bonds underneath it. Okay, it starts forming underneath. So this carbon right here kind of gets pushed up and out of the way, has to get pushed up and out of the way so that this can form. So this is your 6-membered ring. Here's your 1, 2, 3, 4, and then your 2 here, 5, 6. And then this carbon is what's sticking up. Okay. All right, now they're really not showing you that much stereochemistry of these things, but we'll talk about where these are. Okay. Here's another example, but this time you have closed diene. I'm sorry, a dienophile. And notice it's coming out cis. Again, we'll talk all about this. Okay. But for this reaction down here, this carbon forms a bond there. These pi electrons go there, and that one goes there. Okay. To form your 6-membered ring. This is your 6-membered ring, which is right here. And it becomes an alkene. Okay, because these pi electrons go down here to form that double bond. Okay, here's kind of a hint that your book tells you. So a Diels-Alder product always contains 1 more ring than the reactants. So if you don't have a ring, the reaction forms a ring. If you have 2 rings, then the reaction is going to make a 3rd ring. Okay, the 2 ends of the diene form new bonds to the ends of the dienophile. So whatever your diene is, this is just like the classic case. This carbon is going to form a bond with that carbon, and this carbon is going to form a bond with that carbon. Okay, the center, formerly single bond of the diene, this thing right here, becomes the double bond in the product. The dienophile's double bond becomes a single bond, or if this is a triple bond, it becomes a double bond. It's always 1 bond less. All right, let's talk about some stereochemistry. Okay, first of all, your diene must be in the S-cis conformation. Okay, we talked about this last time. Let me actually go up here just to remind you. Remember S-cis, you have S-trans. Remember, it was about the sigma bond. And then you have the S-cis. Remember, this is the S-trans, this is the S-cis. So this is what your diene has to be in. Okay, it's got to be in this conformation. And remember, it's mostly in this conformation, but you do have this equilibrium. Oh, equilibrium is wrong. Going back and forth. But as soon as it makes this S-cis reaction, conformation, it goes ahead and does the reaction. Okay, dienes 1 and 4 p orbitals must overlap with dienes p orbital to form new sigma bonds. Well, I think that pretty much sums it up. I don't think I need to explain that any further. That's a joke. I'm just kidding. It's a little confusing. Well, I'll show you this on the next slide. I believe the next slide has some pictures about this. Okay. Both sigma bonds are on the same face of the diene since stereochemistry. Okay, again, we'll talk about this once I start showing you pictures. Here's the pictures. Okay, so let's see what the pictures are trying to tell us here. Here is the diene. The blue is the diene. This is our diene. Okay, so it'd be like something like this. This is our dienophile. I'll just call it a DP for dienophile. That would just be a double bond. Okay, remember, it has an electron withdrawing group. In this one picture, they're trying to explain all of this stuff right here. Okay, so let me just explain the words in the picture, since that's easier to do in chemistry. Okay, they talk about the 1,4 carbon overlap of the orbitals. Basically what's happening is your p orbitals here and your p orbitals here have to overlap with the p orbitals on your diene. Now this isn't anything new. This is something that you already know. Overlap begins at these orbitals as they come together. We know that if you want to make a bond, it's the overlapping of orbitals. So you have to maximize your overlapping of orbitals. Okay. Now we'll talk about this in a different slide. I want to introduce it to you. But in order to get this maximum overlap, your electron withdrawing group has to be completely underneath all these orbitals. Like if you look, the other option is to have the W on this side, which these hydrogens are out of the reaction, are sticking out of the reaction, where this hydrogen and this W are underneath the blue diene. Okay. Now again, this is very hard to do to explain on a slide, so we will talk more about this in class, but maybe you can kind of get an idea right now. Okay, so there's two sides of our dienophile. You got two groups which are sticking away from our diene, or we have the two groups that are underneath our diene and are having the maximum overlap. You want to have the withdrawing group, all right, overlapping with these our diene. You do not want the W on the outside. You want it underneath, because it's what's called secondary overlap, which we're going to talk about is a stabilizing effect. Okay, so once this approaches your diene, you kind of have this overlap effect, and you want your electron poor. Remember, your W is electron poor. These are electron rich. You always want the most electrons to be interacting with something that has very little electrons. Okay, so that's basically what's happening here. Your overlap starts, all right, starts forming, and you want the most electron poor stuff underneath, so that when it does bond, you'll notice that our withdrawing group always goes down. It's always it's kind of these bonds start forming in these two groups. The two groups that are underneath your diene end up down. Okay, which we will definitely talk much more about this stereochemistry in the next slides. However, at this point, I'm going to stop here, and we're going to start on a new video.